In this lesson, we're going to practice writing and solving exponential equations to model contextual situations. And as we learned before, when we write our exponential equations, we look for our starting value. We also find our multiplier. Then we raise it to the time period that it's being measured in. And multipliers that we've done in the past have been values saying things are doubled, tripled, halved, and so on. But we have to remember if they're talking about percentages, how does that impact our equation? So we have to remember that a percentage is a number based out of 100. And whenever you start a problem, you always have 100% of what you're beginning with. So 100 out of 100 is 1. Then we either add to it to have it increase or grow, or take away from it to have it decrease, decay, or depreciate accordingly. And so if we're talking about our percentage problems, this is kind of the format that we follow. So the 1 again represents the 100% that you start with, and then we add a percentage to that, or we take a percentage away. So again, to remind you that here in this type of format, A represents your final amount, P represents your principal, your starting value. The 1 is the 100% that you originally start with, and then R is the percentage rate that you're either increasing or decreasing by. And remember, that percentage should be out of 100, so it is a decimal value. And then T is the number of time periods that pass, however that's being measured. So if we take a look at our first example here, Lakeside currently generates 86,000 tons of garbage per year, but the city is hoping to use recycling to reduce the amount of garbage by 5% each year. How much garbage will be generated annually 6 years from now? Well, what do we know? They're generating 86,000 tons of garbage per year. They're hoping to reduce it by 5%. So we should have a decreasing situation going on here. And we're doing this for 6 years from now. So again, we underline what we know and we circle what we want to know. Following the pattern that we had before, our final amount of garbage should be calculated by 86,000 tons times 1, the 100% we're starting with, and since we're reducing, subtracting the percentage, well, 5 out of 100, that's 0.05. So 1 minus 0.05 raised to the time period, 6 years. So here's our equation. So if we evaluate this for 6 years, and remember that 6, we should have a caret key here, we can get the garbage amount that will be produced. We also could simplify what's inside the parentheses. If we did 1 minus 0.05, that's 0.95. So we also could use our equation like that, because 100% taking away 5% means you're keeping 95% of the total. So again, either representation is correct. That will tell us how much garbage would be generated, which would be 63,217.9 tons. Here's another example. You purchase a Corvette for $55,495. The car depreciates the value 8.5% each year. How much will the car be worth in 7 years? So again, what do we know? We know the original purchase price of the car. We know that it's depreciating. That means the value is going down. So we're taking away from what we had. And a time period that's being measured is 7 years. We also know the rate, 8.5%. So remember, 8.5 out of 100, well, that's 0.085. So what kind of equation could we write for this problem? Well, the value of the car, let's call that C for the Corvette, 55,495 times 1 minus 0.085, again, losing the 8% per year, for 7 years. Now, if you thought of it in terms of 100% taking away 8.5%, remember that means you're keeping 91.5%, right? This is what it is as a percentage for 7 years. So if we use our calculator to evaluate, the approximate value of the car 7 years later would be $29,799. Not 99, I'm sorry, 0.9999 cents. So we'd only round up to the nearest dollar if this third decimal place here was higher than 5. So again, $29,798.99 after 7 years of buying it. Let's try this one. You place $300 into a bank account that pays 2% interest every year. How much money will you have in your account after 8 years? Well, what do we know about the problem? We're starting with $300 and it's paying 2% interest. So if it's paying, does that mean it's increasing or decreasing in value? That means it's increasing in value. So we're going to be adding to our total. We know that 8 years, we're going to let the account keep the money. So that's our time period. We want to find out how much would be left. So what kind of equation can we write? Well, 300 times 1 plus, right? Because they're paying us interest. 2%, well, that would be 2 out of 100.02 to the 8th power. Or if you think 100% and 2%, that's 102%. So we could write that as 1.02 to the 8th power. Regardless, we should have approximately $351.50 in our account after 8 years. Let's try one more. In 1995, a can of soda costs on average 75 cents in a vending machine. If prices increase about 3% per year, in what year will the average cost exceed $2? Well, what do we know about the problem? We know that the can of soda cost 75 cents when they started this in 1995, and the price increases 3% per year. So we're adding to our amount here. And what year will it cost $2? So we know what we want to end up with. Okay, so we want to end up to see when it's exceeding more than $2. So we're trying to figure out the time period. So let's think about this. We know the price of the can of soda is $2. Okay, so that would go here. The starting amount is 75 cents. We're showing our 3% rate increase, but we don't know the number of years that it will happen. So what could we do to solve this type of equation? Well, we have a couple of ways we could approach this. We could undo the equation and try to isolate our variable t, which is in the exponent. So t belongs to our base. These two items here are being multiplied together. So I could take both sides of the equation and divide it by 0.75 to try to get t. However, t is in the exponent, and we don't know how to get something out of the exponent that's a variable yet. So what else could we do at this point? Well, we know that these two things are equivalent. So think of this as like a system of equations. We know the value one function has to be 2, and the other is represented by our scenario. So this would be perfect to use graphing as a method to solve your system of equations. One equation is your 2, and the other one is what we came up with, 0.75 times 1.03 to the power of t. Now remember, when you're entering this into the calculator, show that t is an exponent. You have to use the caret key, and the calculator only recognizes x as the exponent, so that's what you'll have to type in. So let's show you what that would look like. So for your graphing calculator, you would go to your y equals, and you would type in your function 2, and then what we came up with for the 3% increase for a time period. Now we're going to have to adjust our window. So we have to think about what it represents. X, or t, is representing time. And we know that time is going to start in 1995. So that's like our year 0. And we're going to have to estimate how many years we think that are going to go by. So I press my window key. Let's see a little bit what's happening to the left of 0. So let's go like -5, 2, and then let's estimate, let's go, I don't know, 30. And count by 5, so we can always adjust it. And then our outputs, right, y, that's the price of the can of soda. So we want to see it hit 2, because the question is, when does it exceed? So let's just go from -5 to 5, counting by ones. And again, if we need to adjust our window, we can. Press graph. And for our system, we're looking to see where are they equal, the same place, same time. So we're close. We need to see more to the right of our screens. Remember, we stopped at 30 years. Let's go back to the window here and expand upon that. Let's make that 40 and see if that's better. And we can see when the can is going to be $2. So remember how to find this. We press second trace, option 5 for intersect. Move your cursor close to where it looks like the intersection point is. Again, look, it says first curve, press enter. Second curve, press enter again. Do you want to guess? We don't. Press enter a third time. And it tells you exactly when the price is $2. So that's 33.18. So how long would it take for the can to exceed $2? Well, it would be just after 33 years. So after 33 years of when? Well, this study was in 1995. So we'd have to add the 33 years to our 1995 to figure out when that would be. So if we recap, we had to adjust the window, and we did second trace, option 5 intersect, enter 3 times. We found the intersection point, and now we're going to add that value of x to 1995, which is about approximately 2028, when the can of soda should be more than $2. Now, those of you doing Desmos, you would do the same thing. You would go to your graph feature and enter in your 2 functions. And notice we have to adjust the window. So you can do that one of 2 ways. You can go here and manually adjust it, or you can zoom in and out. Whatever works best for you. And again, to find your intersection point, if you click on your 2 functions, it will tell you where they're exactly the same value. And again, we can see that here, the 33.182 and 2. And again, we add this value to 1995 to get the year that the value of the price of the can of soda exceeds $2. So again, we're going back to what we did before with our systems of equations. If it's something that we can't do by hand, let's use the technology to help solve it for us. So now it's going to be your turn to practice writing and solving your exponential equations in context, and then we'll review to prepare for our upcoming assessment.